You are joining Optimizing for Billions, AWS Cost Efficiency with Tiberiu, Oprisiu, and Sara Reddy from Coinbase. Folks, take it away. Thank you.
Hey, everyone. So my name is Tiberiu Oprisiu. You call me T for short. I am a staff software engineer, part of the Cloud Center of Excellence at Coinbase.
Hey, everyone. I'm Sara Reddy. I'm a software engineer at Coinbase. I've been here for almost 2 years now, where I've been a part of the compute team. We work on building the Kubernetes platform here at Coinbase.
And today we're going to be talking about Optimizing for Billions, Coinbase's tactical approach to AWS cost efficiency. So here you can find the agenda, but to save some time, we're going to jump right into it.
So, Coinbase, who are we? Well, Coinbase was founded in May 2012 and is now the first and only cryptocurrency exchange that is publicly traded and audited. Given this, maintaining trust with our customers is extremely important. As we all know, the crypto market can be pretty volatile, though, and with that, our traffic patterns can change very rapidly. For example, a single tweet from Elon Musk about Dogecoin has the potential to 5x our traffic just like that. But that's something we need to be prepared for in order to maintain this trust. Hey T, do you remember back in February when Bitcoin hit its high after a long time?
Yeah, I remember looking at our traffic patterns, and if you can see the tweet on the screen, we had about a 10x increase in our traffic very quickly because of the market volatility. As a result, it's very difficult to continue serving our customers' traffic when we have patterns like that. That's why during the bull cycles, we focus on scalability and reliability to ensure that we can keep continuing serving our customers. Then during the bear cycles, we shift our focus to cost optimization. That way, when we hit the next bull cycle, we do so as efficiently as possible.
Now, once 2022 rolled around and we were in the midst of the bear cycle, we realized that in order to be ready for the next bull run, we needed to take a more centralized approach when it came to our optimizations, but also when it related to our compute layer.
So a lot of the optimizations that I'm going to mention that we initially did were very manual. That's because we had a short time window to enact these changes, and we had to do so with the tools that we had available. So one of the mechanisms we did is we launched AWS-wide optimizations. And I'll be covering some of this in more detail in a later slide. Essentially, we had a CCoE engineer focus on a specific area, and that's their realm, and that's what they dealt with. Mine was compute. Sara, wasn't this around the same time that compute team was looking into Kubernetes?
Yeah, exactly. During this time, we were starting to build out the Kubernetes platform, and this eventually became a top priority, along with moving our systems over.
So now we're going to go into the AWS-wide optimizations that we implemented. So this was mid-2022. Our leadership had announced to the company that the cost optimizations that we needed to implement were pivotal to the future success of Coinbase. So since we didn't have that much time to enact, and $1 saved now is a lot more than $1 saved a couple of months down the road, we had to enact these changes quickly. Myself, since I was part of compute, the first 2 weeks after this announcement, I was just using Datadog host map view for those entire 2 weeks. Using that service, you can actually filter and group based off the tags within your environment. So since our compute stack was almost entirely in auto-scaling groups, just group them by the name and then the instance type. And then you could see which of your auto-scaling groups had the highest cost just based off the instance type name. Then combine that with the color-coded nature of Datadog host map view, where green indicates very low utilization, red indicates high. We could easily see the low-hanging fruit that we tackled. So within those 2 weeks, we were able to save about $4 million in monthly spend by just going after these easy-to-hit services. Now that we knocked out the easier ones, we had to assemble a list based off of ROI to start working through them. For that, we used AWS Trusted Advisor and AWS Compute Optimizer. Using those mechanisms, we were able to assemble a list of low-utilized EC2 and auto-scaling groups, underutilized or over-provisioned EPS volumes, and underutilized RDS instances, to just name a few. Obviously, this mechanism is very manual, and a month down the road, the list that you assemble could be out of date. Sara, don't we have a better mechanism for this nowadays?
Yeah, exactly. Once we moved over to a more centrally managed system, it was easier to do some of these things in a more automated fashion. We'll soon see how we were able to do this for compute utilization in particular.
Another item that we actually did was the manual purchasing of reserved instances. We had an engineer on a monthly basis perform these math problems and go on the AWS marketplace and pre-purchase the reserved instances that we need. Eventually, we ended up working with ProsperOps to automate this and ensure better coverage for our reserved instances. So as I mentioned, we had a CCoE engineer focus on a specific area. It all depended on which had the highest ROI for our company, because we had a very limited time to enact these changes. As I mentioned, I was part of the I was part of the compute layer, so I was focused on EC2 and auto-scaling groups. We had another engineer working on RDS, Aurora. We had someone else, Elasticast, S3, Amazon MSK. It all depended on where we had the most money we were spending and which had the best ROI for our team. At the same time, we actually had a top-down and bottom-up approach. Our leadership had announced to the entire company how pivotal these cost optimizations were for the future success of Coinbase. So now that we had leadership buy-in, we worked with the actual engineers that manage these services to implement these optimizations for them, show them the drastic changes in cost savings they can achieve by just modifying a couple configuration options. Now, using these success stories, we would share them across the company with self-service guides, so these engineers now knew that they could enact these changes themselves without having to contact a CCoE engineer to perform these changes for them. And obviously, with one engineer per focus area, we needed a way to horizontally scale this work, and using those mechanisms was the best way to achieve that.
Additionally, once we moved to Kubernetes, a lot of this helped lay the groundwork to do so.
So now we're going to go into the crawl phase, which is our auto-scaling group optimizations. So to do this, we looked at compute efficiency across the stack. First, we looked at infrastructure efficiency. And I'll be covering this in more detail, but some of the items was just improved scaling policies. So our auto-scaling groups could scale out faster based off the metrics. Then there was increasing metric granularity. We had a couple settings in our infrastructure stack which indicated how often the metrics were being looked at by auto-scaling groups. There were some configurations that need to be modified, and then we also had to improve what was available to our engineers. Then was application efficiency. As we began increasing the utilization across our services, we ran into different bottlenecks. Luckily for us, we had Datadog Continuous Profiler, which could show us exactly where the CPU cycles are being spent by our instances. So as you increase utilization, you should expect your latency to go up as well. But a 10x increase in latency by going from, let's say, 5% to 30%, that is not normal. But with Datadog Continuous Profiler, you can see exactly where those cycles are spent and what is impacting your latency. Next was engineering efficiency. As I mentioned, our engineers just didn't have the necessary knowledge or tools before this hand to implement these changes themselves. But with these self-service guides and the success stories, they now knew that they can implement and optimize a service without having to just over-provision to get over a problem. So what did we do for auto-scaling groups? Well, we looked at our scaling process holistically to identify bottlenecks. On the top right-hand side, you can see a chart that indicates the scaling process. On the left is time until identification of a scaling event necessity. What that means is how long will an auto-scaling group know, how long will it take to know that it needs to scale out? To improve that, we implemented a couple changes. First was adding step scaling policies. That's a feature from AWS. So beforehand, we were actually using target tracking to scale the majority of our services. What you may not know is target tracking is inherently slow. It will take 3 data points before it makes a decision on how to scale out and how much to scale out. So in a very volatile market, 3 minutes after your metric is breached, you could be close to 100% CPU already. So that is not, we needed a better mechanism. So combining target tracking with the step scaling policies, we could handle the surges in traffic using the step scaling policies, while target tracking handled the gradual upscale or downscale of our services. That made a massive difference in our scalability. Then was improving metric granularity. As I mentioned, we had the capability to set metrics to emit at 1 minute intervals, but we needed them to be better. So I worked with observability to bring that down to just 10 seconds. So within 10 seconds of a metric breach, we could have an auto-scaling group ready to launch new servers to handle that increased traffic. Now on the right-hand side of that top chart is you have time until newly launched servers are bootstrapped and begin taking on traffic. That is how long will a server take to become healthy and actually begin serving traffic for your customers. Up until that point, the engineers didn't really focus on this metric. They would just always set a lower CPU target to provide the buffer so it can scale out. With AWS auto-scaling groups, rather warm pools, what that feature does is it will launch a server, wait for it to get bootstrapped, and then put it in a stop state in that warm pool. Afterwards, anytime we need to scale out, it would prefer to use those pre-initialized instances than a new instance that it was just launched. As a result, we actually saw a massive reduction in our boot times. And believe it or not, this is actually not an expensive feature. When an instance is in a stop state, you're not paying for it. So the cost of this was just 5 minutes of boot time and then whatever EBS volumes you have attached to it. And that made a massive difference in our scalability. Now, with all of this combined, we enabled sub-minute scaling for our services, which is extremely important in volatile markets where a tweet from Elon Musk can 5x our traffic. Next, we had the company-wide rollout of all of these infrastructure changes. So what are some of the challenges we encountered? Well, as I mentioned, as we increased utilization across the services, we identified additional bottlenecks that we had to deal with. Luckily, a lot of these bottlenecks just had some configuration changes we had to implement. For example, Golang garbage collection. You may not notice, but Golang is very aggressive when it comes to its garbage collection. If you're operating at a very low latency, the higher you increase your utilization, with Golang garbage collection not configured, it will just operate it'll eat up your CPU cycles, resulting in higher latency for your actual customer requests. With the new versions of Golang, this can be just modified with environmental variables. So again, a configuration change that just allowed our services to operate at a higher utilization while actually achieving a lower latency than they had so beforehand. Another update was related to AWS SDK use cases. So out of the box, the AWS SDK has a really low idle connection count, only 2. So if you're operating at low latency, you don't want your service opening and closing connections because of that setting. So this was just another configuration change that made a massive difference for our services, which also contributed to lower latency and the ability to operate at a higher utilization levels. Then we had to ensure that we are making our services stable while continuously pushing the limits. This had a lot to do with our load test team and some features that they launched while we were optimizing our services, and we'll go into a little bit more detail about that in a later slide. Finally was overcoming cultural barriers. As I mentioned, our engineers just didn't have the necessary knowledge or tools beforehand to understand how they can optimize their services. So we were always over-provisioned to just handle these surges in traffic because they did not want to take the additional risk of their service going down. But now with the self-service guides and the updated infrastructure, they were able to optimize the service and save costs while becoming more performant. Sara, don't we have a better mechanism for this?
Yeah, exactly. Like I previously mentioned, after moving to a more centralized ecosystem, we had more control. We could more easily apply some of these optimizations at a global level, and we'll soon see how.
So what are some of the results of this? As I mentioned, we're able to enable sub-minute scaling for our Golang services. This was key. Actually, remember, there was a service that I applied this to, and a couple weeks later, they were DDoSed. Within a minute, it scaled up and actually was able to handle that DDoS traffic while still serving our customers. Obviously, we don't want to scale up when we get a DDoS, but in that situation, it helped ensure stability for our customers. Then, our legacy compute stack, or rather our legacy language, is Ruby. You may not notice, but Ruby is pretty slow to start up and boot. But with warm pools, we were actually able to cut that down to half of without a warm pool instance. I remember when I started working with our monolithic Ruby-based application, Without any of these updates applied, it would take about 15 minutes for it to go online and start handling traffic after the metric has been breached. With these updates in place, we got it down to about 3.5 minutes. It's a drastic difference. So with all of these optimizations implemented across our services, we're able to 2x our CPU utilization on average across everything and achieve a 75% cost savings.
Now, how could we further improve this? How could we decrease boot time, increase CPU utilization, decrease cost, and do so in a more automated fashion? Well, the move to Kubernetes helped facilitate this. So now we're in phase 2 of compute efficiency, Kubernetes. We're now in the walk stage. We have learnings and lessons to draw from when it came to efficiency. So in this section, I'll first be going into the advantages of Kubernetes. Next, I'll go into the inefficiencies we still saw, and finally end with how we aim to address these from a cultural and technical standpoint. So here are some of the advantages of Kubernetes over our legacy ASG system. I'll be going into efficiency, scalability, and centralization. So first, on to efficiency. In our previous system, services and hosts were one-to-one. But in Kubernetes, we could now bin pack services across a shared pool of hosts. Because of this, resources could be used a lot more efficiently. Otherwise, we were left with a lot of unused space on these hosts. Additionally, in Kubernetes, you could have more granular resource settings. So for each service replica, which is called a pod in Kubernetes, you could set a specific amount of CPU and memory, which gets allocated to it on the host. Now, as a result of moving to Kubernetes, we saw about a 68% decrease in our resources. Next is scalability. So in Kubernetes, you can also scale a lot faster. And this is because in the ASG world, for each new replica, we needed a new host, which can take up to minutes. In Kubernetes, for each of these services that scale up, when there's existing capacity on our hosts, scale up can happen in seconds. Now, in Kubernetes, we didn't get rid of over-allocation altogether. Instead, we aimed to over-provision at a global level rather than the service level, so we needed less. Now, the last area I'm going to focus on here are deploy times. In Kubernetes, we saw much faster deploy times. This doesn't just mean developers save time, but it also means quicker incident response and incident mitigation, and in our industry, that translates directly to cost savings. So as a result of this move, we saw about a 80% decrease in deploy times. Next, I'll get into the benefits of a more centrally managed ecosystem. So components of the base stack could be managed and run by infra teams, which helps remove this burden from service owners. Additionally, there are managed Kubernetes offerings, such as EKS, or Elastic Kubernetes Service, which is provided by Amazon. So these provide a lot of benefits. For example, areas like maintaining and securing the control plane is handled by them. We don't really need to worry about this layer. Additionally, there are a lot of add-ons and integrations that come right out of the box. Now, lastly, there are a lot of open source solutions and vendors out there that are built up specifically for Kubernetes. By leveraging these, we can use industry standard tech and save time that would otherwise be spent building in-house custom solutions. And as a result of all these, we saw less operational burden. Now, despite all these great improvements from just moving to Kubernetes, we weren't quite operating efficiently yet. And this is because bin packing did not guarantee service efficiency. There was nothing stopping service owners from requesting way more CPU than they actually needed. So this needed to be addressed. And as a result, utilization was pretty low. So to the right is a table of some of our more underutilized clusters. These are CPU buffer percentages. So this is essentially CPU that is being requested but not used. And as you can probably tell, these numbers aren't great. So we needed to do something to address this. The second part of this problem came from the mindset around over-provisioning. This is what service owners had been used to, and also due to concerns around being prepared for the next bull run, as that was kind of imminent. And it was a lot safer to over-provision. So once again, we needed to do something about it. So after identifying some of these inefficiencies, we aim to address them. These are 3 of the focus areas that came up. First is optimized CPU utilization. So in order to help reduce these buffer percentages that we saw, we needed to reduce CPU requests and increase scaling targets. Additionally, we also use shared buffer capacity. Hey T, how is this different from the excess capacity we used in the ASG world?
So with auto-scaling groups, each individual service owner determines how much buffer to have, which is not ideal, especially if you have a market event about to happen. We can't be expected to launch 1,000 PRs to update the settings for our engineers. But in Kubernetes, now we have that shared buffer at the cluster level. So for example, we had a Bitcoin ETF launch. We could just manually pull that lever and increase the buffer for our clusters, and then all of the other services within that cluster can use that shared buffer equally.
The last area is load testing and monitoring. Now, in order to truly build the trust with service owners, we needed to have the tools to validate scaling and performance at bull market traffic levels. So let's dive deeper into the first area. Services were requesting way more CPU than needed. Now, the reason for this is because it was time-consuming to figure out what are the right resources to request, and it could change a lot over time. So this proved to be burdensome for service owners. Additionally, there was also a lack of visibility into what optimal resources would look like and that they were inefficient in the first place. To address this, our solution was automated pod right-sizing. This solution essentially automated CPU requests at deploy time, and it did so based on recommendations that were based on historical usage. Now, let's get a little bit deeper into the architecture overview. I'll walk you through it. So at the top, we see that users can initiate a deploy, and then our deployer will reach out to our right-size API that we created. This API will generate recommendations based on historical usage. Now, to help compute these, we actually use the savings endpoint from a vendor called KubeCost, which has been great. So after these recommendations are returned back, the deployer will override the user set requests and use these instead. Now, another focus area with this design was making sure we provided flexibility for service owners. We wanted to give them options. If they didn't want to be involved with their CPU requests, they didn't really care what it was, they could sit back, let the right sizing do its job. If they did want to, however, we gave them the options and levers to do so. For example, users could opt out of this entirely and choose to manually right size. We wanted to make this as easy as possible, so we provided them with options. We exposed the right size API manually, so they still had access to these recommendations. Additionally, after each deploy, whether it was done via the CLI or the UI that we provide, these recommendations were displayed so that they knew that they were there. Now, another area that we focused on with flexibility was allowing users to dial up and dial down the right sizing, and this was especially useful for new services where maybe the historical data wasn't accurate yet. Now, as a result of these efforts, so far we've seen a 10% reduction in our total compute costs. So, in order to truly shift the mindset around over-provisioning and promote efficient scaling, these are some of the other areas that we addressed. So first is best practices. We needed to adhere to Kubernetes standards and best practices and ensure that service settings were optimal for fast scaling. To do this, along with creating internal guidance, we automated a lot of these settings where we could. We wanted to make sure that these pods could get up as fast as possible. Now, the second area is load testing.
So this was actually key in the AHG world as well. As you can imagine, increasing the utilization for our services, we needed to tell our engineers that they could do so safely. For that, our load testing developed scale-in load testing. Using a CLI command, it would actually launch a new server or pod, and then it'll begin shifting production traffic to that single pod or instance until it hits a predefined threshold. At that point, it'll just monitor for the next 5, 10, or 15 minutes, whatever is configured, and then you can gauge how your service will actually operate at that utilization level prior to enacting the change for the rest of production traffic. Then, when it came to our Kubernetes migration process, we developed a mechanism where we could send load test traffic only to our Kubernetes pods, while auto-scaling groups are still serving traffic for our production customers. As a result, we can continuously and safely iterate through the changes in our Kubernetes pods until they are ready for the production cutover.
Additionally, we wanted to make sure that our service owners had the proper observability. So along with out-of-the-box metrics like resource usage, pod count, we created some custom metrics around startup times. For example, we specifically created metrics around scheduling delay and pod and container readiness times. That way, customers had insight into this. Now, this helped a lot during load tests. We could better see where are the constraints and whether it's happening at the service level or a global level. Additionally, service owners could monitor these metrics and look for any regressions when it came to startup. The last area I want to focus on is preemptible pods. So as we've kind of mentioned through the presentation, we wanted to over-allocate at a global level rather than the service level. And that's what these pods did. They were essentially a lower priority service compared to our regular Coinbase services. So what this means is that during high traffic times, when maybe all of our existing hosts are at capacity and we're waiting for new ones to spin up, these preemptible pods will be evicted in favor for regular services. And this helped a lot with their scale-up times. So this table should look familiar. It's those 4 clusters I showed earlier. And as we can see, the buffer percentages had significant improvements. One decreased by as much as 57%. Now, these numbers are a lot better, but they still could be even better. So we're continuously optimizing and looking for ways to improve our efficiency.
So now we find us on the precipice of the next bull run. As you can see, Bitcoin price has gone up, and so has our volatility. But gladly, we're now running on Kubernetes, and we can run so operating efficiently and effectively at scale.
Additionally, like I mentioned, we're continuously iterating and optimizing. And with this, we'll find new solutions.
So as you've probably heard multiple times during this conference, you're never truly in a run state. There's always something around the corner that's going to throw you back into walking. So that's why it's very important to always look at what's your next improvement and how you can keep pushing the envelope further. And Sara's going to cover some of our future looking optimizations.
So here are a couple examples that we think could help take our efficiency and scalability to the next level. I'm not going to go through all of them, but I will focus on a few. The first one I want to quickly touch on is memory-based right-sizing. I want to call this out specifically because we've only really discussed CPU-based right-sizing. Now, this is still an important area, though. The main reason we focused on CPU is because, first, it's more expensive, but also because it's easier to right-size. Unlike CPU, memory is not a compressible resource. It's not as easily freed and taken up compared to CPU. Additionally, with memory, there's additional caveats like out-of-memory errors that you can potentially run into. So doing this requires more caution and guardrails, but will likely need to be a focus area for us. The last area that I want to touch on is dynamic provisioning and better host management. So we haven't done a lot with this yet, but there's a lot of benefits we can get from doing so. There's also a lot of unknowns here. So, for example, solutions like Carpenter can pretty effectively analyze your needs in compute, how many nodes you need, and what instance types you need. So you can use your resources a lot more efficiently. Additionally, these types of systems can have a lot of settings when it comes to scale up and scale down and faster scale up times. So there's a lot of benefits this can provide. Now with that, there's a lot of solutions we can explore, and as we continue to adopt them and continue to reach new traffic levels, we'll also inevitably run into new problems. And with those problems, this kind of cycle of iterating will continue. And because of that, we're never truly running. Now with that, I'm going to open it up for questions.
I see a lot of hands. I will attempt to go left to right for the moment. Starting right here.
Hi, thanks guys. Really great presentation. We had have a situation in our company where We run out of memory, but we have lots of CPU left for our pods. So we have like 15 to 20 different clusters in various different regions. So we are struggling to find a solution where we have CPU and memory both available for our pods on all the clusters. Have you seen this situation in your company? Thank you.
So you're saying your CPU usage is a lot higher compared to memory?
The other way, memory is.
Oh, memory is.
CPU, yeah.
I guess we haven't run into this too much. I feel like the biggest area would be like improvements in instance types, which I'm sure you've probably already looked at. And like better node management solutions like Carpenter can help optimize for this because it can help see that like memory is the resource that's being constrained. But otherwise, I don't think we have dealt with this too much.
Yeah, I was going to just double click on the Carpenter. That would be the long-term fix because any kind of manual changes in your instance type are going to get outdated a couple months down the road if your engineers change what their pod size requirements are going to be. So anything automated is going to be the best solution to go, and Carpenter is a great option for that. And I actually know there's a couple of vendors out here that have similar-ish solutions. So I would highly suggest talking to them and just seeing if Carpenter can fit what your company needs.
Sure, guys. Thank you.
Hi, thank you for your great presentation. I had a couple of questions. I'm from the finance side of the house. So when you did global level resource, like, getting the buffer there, right? What was your allocation methodology for the global, just like overall, like how did you use that money to allocate to different services? And also, like, just asking on, I forgot the question. Okay, just, yeah.
Our company load tests very frequently, typically on a weekly basis, sometimes multiple times a week, depending on the situation. So when it comes to the pre-allocation of the buffer, that's kind of determined by the load test team because they look at our traffic patterns over the historical period and determine what we should be load testing based off of other surges in traffic that we've experienced. So it's not as much of a finance problem, but an engineering problem to set what we need to set it to. So we continue to serve traffic to our customers irrelevant of what may happen in the market.
And how about forecasting? Like, because you've done such a huge, great effort on Autoscale, like, how do you know where you land your numbers, like for the quarter, or like, is that a challenge or not really?
Yeah. So I'm laughing because our FinOps team is actually sitting in front of us here, and they're currently tackling that problem. As you can expect, our traffic patterns are not predictable. A tweet can 10x traffic, so it all depends on what models they're using, and I know they're kind of working through that at the moment.
Hi, really good presentation. Thank you. Question I had was this right-sizing API that you use for right-sizing. Is that something you guys developed, or was it?
Yeah, so it is something we developed. For part of computing it, we do use a vendor called KubeCost. They have like a savings endpoint, but we have additional validation and stuff that we do there too. So yeah.
So that you just use the endpoint to just gather data, but you don't necessarily need KubeCost, right?
Yeah, I mean, I guess you could use whatever methodology you want. We just found that that worked well for us.
Okay, thanks.
Are you guys using the warm pools for the nodes as well?
We're not using warm pools for Kubernetes. I've actually spoken to the EKS team about that, and their opinion is that the EKS doesn't need that. Technically, our nodes do scale up pretty quickly, and we're looking forward to moving to Carpenter, which can reduce that even further.
We should talk. I use Carpenter in production today, so.
Yes, let's connect.
A little more technical, but are you using one big EKS cluster, or do you have workloads split across multiple?
We have workloads split across multiple.
So you were able to reduce your CPU buffer quite a bit. It's pretty impressive. I would think you would see a little bit more like cost savings. I think it was like 10% CPU or cost reduction, whereas the buffer reduction was like sometimes 30%, maybe close to 40%?
Yeah, so the cost savings were specifically attributed to our automatic pod right sizing, but the general efficiency is all of the efforts we saw, which might include better scaling targets and other practices like that.
Thanks.
Hello, thanks. Have you noticed any specific challenges yet with Carpenter or using spot instances?
So we don't use Carpenter yet, but it is something we plan to try to use because an issue we do see is we need better node management, faster scale-up times, and better usage of our instances. So that's why we're looking to adopt Carpenter.
Okay, got it. Thanks.
Do you guys have any tips for motivating engineering teams to prioritize optimization coding over features?
What worked really well for us was actually the sharing success stories on Slack and just having a visual representation of how they can see the cost savings. Because in all honesty, if you can make a configuration change and you can see your costs go down by 90%, anyone's going to be excited. Especially if you have your leadership telling the rest of the company that we need to go and focus on cost optimization if we want Coinbase to continue to be a successful company.
Along with this visibility, I think it's also important to try to automate things where you can and make it as visible and easy for service owners. Like, for example, for the automated pod right sizing, even if they were opted out, we still show them the recommendation so they could be like, hey, let's try that out or kind of look into it more. We wanted to try to make it as easy as possible to do this.
5 or so minutes left for any burning questions. Yeah, I see one here.
Hi. I just wanted to ask a little bit more about that right-sizing API that you developed. I think you mentioned machine learning. I was just looking for a little bit more info on that and why you decided to develop it in-house rather than look at a vendor.
Yeah, so we do have an insight, and we did build an API in-house, but we also rely on a vendor. So the in-house one is so that we could change it however we like maybe we decide we want to do things differently. It makes it easier to have a separate API, and we could also do additional cleaning. If we find anything that's not working so great with the vendor, we can see how we can adjust it on our end ourselves. So there's really not a lot we do with the API, but it's nice to have it built out and separate so we have the option to do so in the future.
Are you still using RIs with your Kubernetes deployments or a different strategy now?
We still use Prosper Apps for our RI coverage. Ideally, we'd like to have a mechanism where our Kubernetes nodes, or rather Kubernetes clusters, understand that we have unused RIs and then use those instead of on demand. But that's in the works.
Hi, Sara. Thank you very much. Round of applause.
Thanks for watching. Check out more FinOps X 2024 content on our YouTube channel on the 2024 playlist. Support our channel by liking, subscribing, clicking the notification bell, and by leaving comments and questions for our speakers. We appreciate your support.